Hello, and welcome to another episode of the Book Club. Um, Last time we kind of took a little digression from the usual computer organization and design, and we took a look at the 1946 paper from Burks, Goldstein, and von Neumann. Which was a very interesting read, but I believe it is time to get back to computer organization and design. So let me open up Milton here, and we're going to be doing the exercises at the end of the chapter here. So we read chapter 1, and there is section 1.13 exercises that we're going to be going through. And it doesn't look like they have answers in the book. They have answers to the check yourself at the end of the chapter here, but not answers to the exercises. And I don't think there are answers in the back. We've got an index. Appendix exercises. So there's exercises for this last appendix, it looks like. So that's Appendix A. If we go through here, still in Appendix A. And before that, it looks like we have chapter 6. So yeah, they don't put the answers to the exercises in the book. I imagine there's like a teacher's edition of the book that has that. Let's just check the website. Supplements maybe. Advanced content, glossary, index, further reading. Is my browser frozen here? And it crashed. It's kind of amazing that we live in 2017. And we don't have stable browsers yet. Okay, I'm just going to put this over here. Let me line this up for you guys. Instructor Materials. So can we get Instructor Materials? To be an approved instructor, it looks like you would need to be a part of an institution. And I am not a teacher, so I would not have access to this then. So I don't know if anyone finds like instructor materials that are freely available let me know, but I don't think I can access any instructor materials. So here's what we're going to do. We're going to do kind of like a peer review thing. So I'll work through the exercises still. But of course, I might get, answers wrong. I have no idea if I can't check the answers. So people in the community can, if you follow along with this series and you're interested, you can do the exercises yourself and compare answers and discuss on an open forum, right? So either in the YouTube comment section or on forum.risky.tv. We should probably make like an official place to discuss exercises from the book. So let me do that right now. I'm going to go to forum.risky.tv. All right, and we're going to do a new thread here. So it looks like I'm going to need to re-log in. So handmade-network. All right, and new thread. So here is a thread to peer review my answers to COAD 1.13 exercises. I'll post the video here when it goes public. All right, so this is going to be the official place to go and discuss the COAD 1.13 exercises for the book club series that I do. So if you're interested in that and want to discuss these exercises, like I say, go to forum.risky.tv and find the COAD 1.13 exercises thread. That is where we will be discussing this. But for now, of course, it's just a placeholder because obviously I have not done it yet. So let me see here. So I mean, let's just go down here. We might need to reference the performance equations, I'm guessing, so maybe I should leave it up here. All right, let's dive into the actual content now. All right, 1.13 exercises. The relative time ratings of exercises are shown in square brackets after each exercise number. On average, an exercise rated 10 will take you twice as long as one rated 5. Okay, so they do give you some kind of hint as to how long these are going to take. I don't know if like 10 means it might take 10 minutes or what. But they say like 10 will take you twice as long as one rated 5. Sections of the text that should be read before attempting an exercise will be given in angled brackets. For example, section 1.4 means you should have read section 1.4 under the covers to help you solve this exercise. So we read all of chapter 1 already, so we might need to reference stuff from what we've previously read, but it's not like we're diving into these exercises before reading the chapters, so I think we're good in that regard. So let me just go through the time hints that they give, the time ratings or whatever. So how many exercises are there? So it looks like there are 15 exercises. Some of them are split up, though, into like multiple exercises. So 1.1 has a time rating of 2. 1.2 has a time rating of 5. 1.3 has a time rating of 2. The next one has a time rating of 2. Then there's one that's 4. Then there's one that's 20. One that's 15. And then 1.8 here is split up into multiple. So there's 1.8.1 is a time rating of 5. 1.8.2 is a time rating of 5. 1.8.3 is 15. 1.9.1 is 5. 1.9.2 is 10. And then 1.9.3 is 10. 1.10, we have one that's 10 and 3 of them that are 5 each. 1.11, we've got 5 of them that are 5, a couple that are 10, another one that's 5, and I guess we went into 1.11 here. This is 1.11. 3 of them that are 10, one that's 5, one that's 10, 10, 10. Here's one that's 5, 5, 5, 10, 10, 5, 5. So, like I say, I don't know if they base these measurements on like minutes or something. I don't know how they came up with these time ratings. So I guess we'll see how long it takes me to go through these exercises and maybe get a feel for it, right? But let's dive into the first problem here. So 1.1, aside from the smart cell phones used by a billion people, list and describe 4 other types of computers. This had a time rating of 2. So it says list and describe. I don't know like how much they really want you to describe, but I mean, like if this says a time rating of 2, I'd think that means like 2 minutes, but you can list off 4 different types of devices in like 2 seconds, right? So I don't know. I mean, this is like a college textbook, so maybe they expect you to, really go into the descriptions of each or something. But so they gave smart cell phones as an example, smartphones, and they say describe 4 other types of computers. Okay, well, we've got desktops, we've got laptops, we've got, maybe you could count those as one. I don't know. There's tablets, which are kind of like smartphones, right? You've got servers, you've got embedded um, systems, you've got what else? I mean, like, I guess kind of on the server end, you could say like supercomputers. Um, uh, what else? Like, I mean, embedded is kind of that covers a lot. Because like you could say, well, the computer in your car, for example, but that would be embedded, right? Um, so I think we kind of covered everything there. Like 7-ish things if you're counting smartphones too. Um, I'm trying to think, is there anything else? Um, any other like major kind of computer today? I mean, like maybe you could count like quantum systems. There's like D-Wave. Um, they make those quantum computers. They're not like a proper quantum computer. They use like I don't know what it's called. I'm not like a quantum guy. I don't know the physics and all that, but like they use a type of thing that like there's quantum effects in what D-Wave does. So D-Wave, if you don't know, is this company that makes these computers that are supposedly like they brand them as quantum computers, but um, they're not like I guess the jury is still out on the type of quantum effects that are happening in their machines. If those kinds of effects can actually give like a quantum kind of speed up um, over a classical machine. Whereas theoretically, we know that quantum computers, there are algorithms that you can run, like Shor's algorithm for prime factorization or something like that. Um, and that can run faster than what we can do classically, right, with a classical machine, just theoretically, um, using quantum computing. But then we have D-Wave, and they're doing something that uses quantum effects, um, but it's like not the kind of quantum computing, like not the real deal. And like I say, I don't follow the specifics because I'm not a quantum physicist. Um, so it's quantum annealing. I don't know if I'm pronouncing that right, but that's what they do. Um, so a quantum annealing processor, and that's distinct from uh, kind of what people think of when they say quantum computer, apparently. But that you could say this is another type of machine. Um, I don't know if you guys know Linus Tech Tips. I know I'm going way over the 2 minutes here, but we gotta have fun here. So like here you can see I've probably been watching Linus Tech Tips that it shows up. Uh, um, this guy did a I don't know if I can find it here for you guys. He did a like a tour of the D-Wave, um, like their business headquarters or whatever, and that's really interesting. I want to find the video for you guys if I can. I'm not going to play it, but I just want to show you guys. Because that's kind of an interesting kind of computation that you don't, usually think about, but uh, that's another kind of computer, so to speak. Although really, I kind of think, talking about a quantum computer, and this is it right here. I think this is kind of different than, a quantum computer. Like they have these dedicated, these quantum annealing like machines, but really, quantum computers are for solving like kind of specific narrow problems. They're not really so much general computing machines. And I kind of relate that to, GPU versus CPU, where a GPU is really kind of specialized for doing these really data parallel problems, and a CPU is more of a general purpose computing device. And we have them both in what we would call a computer. They're both computing devices. You could say the processor of a GPU architecture and one of a CPU. Those are two different types of computers in a sense, but we have them in one machine, and we call that one machine a computer. So it's kind of an interesting question of semantics too, because you could imagine, having like a quantum coprocessor, in the future, like kind of like a sci-fi, type of thing, where you have in your computer in a PCI slot, there's this quantum device, and you use it for, cracking encryption, right? That's kind of the place that I see quantum computing is fitting into, just kind of like a specialized subdomain of computing. But yeah, this is a cool thing to check out. This kind of little tour that Linus takes here of this D-Wave company. So yeah, check that out if you're interested. But yeah, that's pretty much all I can think of the different types of devices we have around us today, for kind of the different forms that computers take. And with RISC-V, to tie this into RISC-V, there's really, now that the kind of the marketing that Sci-Fi does, what they're trying to do as a business of providing, so that instead of getting a pre-made CPU, now companies can go and say, we want to build specialized hardware. So a great example of that is in the field of deep learning, which is taking off these days, of course. In deep learning, it's common today to use GPUs, but there's also interest in specialized hardware for deep learning as well. And that's kind of the thing that Sci-Fi is saying, like, well, you can take our, platform here and customize it to your needs and have, a custom kind of system to do your specialized workloads more efficiently than a more general off the shelf kind of solution. And that's maybe the direction that the future is headed in terms of the forms that computers are going to take. There might be a lot more of kind of specialized machines for, doing one job very efficiently. One company I want to shout out that was acquired by Intel, Nervana, and apparently they've rebranded as Intel Nervana now. If this is the site I'm thinking of, I don't know. But these guys do really cool stuff. When I was looking into deep learning at my previous job, I saw what these guys were doing, and it's really interesting. So they're doing custom hardware is why I brought this up, this company here. So I don't know if we can even... But, you know, you see the marketing here. This seems like just a marketing site. There's not really interesting stuff. I feel like I remember when I checked out Nervana, they had been acquired by Intel, but they didn't have like an Intel rebranded site with all this marketing nonsense. They had a lot more interesting stuff. Like they had a link to their GitHub of like this platform that they built, kind of like TensorFlow or things like that. They built their own, and I believe they were using NVIDIA GPUs, and they actually like were doing crazy stuff like reverse engineering the hardware and like writing machine code for the GPU to get like really good performance. It was really interesting, the kind of stuff that they were doing, and they talked about on their website the kind of hardware that they were interested in making too, like making custom hardware for this kind of workload. And you can see here from the marketing, a new class of hardware that is AI by design. So obviously that's what they're talking about here, but you know, this is all just marketing nonsense. Nothing really talking about the specifics. And I take it the Nervana platform would probably be like the stuff I was thinking of, like the GitHub that I remember seeing before. But I don't know. That was just something that crossed my mind. Let us continue. So I think we've pretty much beat 1.1 to a dead horse. Like, we've definitely gone above and beyond the list for types of computers, I think. So let's move on to 1.2. The 8 great ideas in computer architecture are similar to ideas from other fields. Match the 8 ideas from computer architecture: design for Moore's law, use abstraction to simplify design, make the common case fast, performance via parallelism, performance via pipelining, and performance via prediction, hierarchy of memories, and dependability via redundancy, to the following ideas from other fields: assembly lines in automobile manufacturing, suspension bridge cables, aircraft and marine navigation systems that incorporate wind information, express elevators in buildings, library reserve desk, increasing the gate area on CMOS transistor to decrease its switching time, adding electromagnetic aircraft catapults, which are electrically powered as opposed to current steam-powered models, allowed by the increased power generation offered by the new reactor technology. And finally, building self-driving cars whose control systems partially rely on existing sensor systems already installed into the base vehicle, such as lane departure systems and smart cruise control systems. All right, so those were labeled A, B, C, D, E, F, G, H, and were to match each of them up to the 8 great ideas. So I'm not going to bother writing this down in Milton, but let's just go through them one by one. So A is assembly lines in automobile manufacturing. I'd call that pipelining, right? So performance via pipelining is what I would say for that. Suspension bridge cables. That's a more interesting one. So suspension bridge cables. I don't know really how bridges work. Like, what is the function of suspension bridge cables other than like suspending the bridge in place? I mean, like, they don't, do they serve to, like, structurally support the bridge? I mean, like, uh, suspension bridge cable. Like, tell me the function that a suspension bridge cable serves. So a suspension bridge is a type of bridge in which the deck, the load-bearing portion, is hung below suspension cables on vertical suspenders. So, like, I don't see, like, structure below this bridge we see right here. Um, like, you think of, like using triangles to support, to distribute the weight, and it's, an efficient structure. Like, I think they're doing that via the suspension of, like, the cables. Like, that's taking on the weight. So is it actually the structural support is what I'm thinking. So vertical suspender cables carry the weight of the deck below. So yeah, like, that's the job of the suspender cables. And it says it's constructed without false work. So I think false work, I don't know if that means like framework that you put up while you're, like, temporarily while you're building, or if it means like the structure below the bridge that supports it. I'd imagine they mean like the structure below the bridge that supports it. That's what it looks like here. Like, you see the structure here. Although it says it is temporary structures used in construction. So it's not actually the part that's in the final bridge, but it is serving that purpose temporarily. I gotcha. So I'm thinking, like, when I'm thinking suspension cables, so we're mapping this to the 8 great ideas of computer architecture here. I'm thinking, like, what is that serving a purpose of? What is the purpose of these suspension cables? I would say it's the structural support of the bridge. It's holding the weight. Um, so what does that map to? Um, it could be dependability via redundancy, such as, like, if, see, like, you see this picture here, like, this tower here, clearly there is, like, structural support, and you see the triangles along the actual bridge deck below it, right? Like, on the side here. So it could be that the bridge does have structural support without the suspension cables, but that the suspension cables are providing redundancy. Um, like, I just don't know because I'm not, like, a bridge builder. uh, is that what they're going for? Maybe. So let's see the advantages and disadvantages here. Let's just read a little bit about bridges. So, longer spans are achievable. So this is one point. Less material may be required than other bridge types. leading to reduced construction costs, you could say it's a simplification thing. Like, you could say the appeal here is that it's simplifying the design. And maybe that ties into like use abstraction to simplify design. Like we're saying the suspension cable design is the form of abstraction being used to simplify the design of a bridge or something. Maybe. I don't know. That's one idea. Those are the only two that really stick out to me as making sense for suspension bridge cables. Either dependability via redundancy or use abstraction to simplify design. That's kind of what I'm thinking here. Like I'm not seeing anything in here talking about like using cables for redundancy. Like you could have like multiple cables, so if like one cable breaks, there are others that are doing that same job. So they could, you could definitely design a suspension bridge with redundancy, I would think, but I don't know if that's like a defining feature of a suspension bridge. So I still don't know for sure what they're going for on this one. But I'm sure each of these, like A, B, C, D, E, F, G, there's eight choices. Like there's eight points here, and there's eight ideas. So I imagine they all map to a unique one. So we can probably figure out what the correct one is by elimination, right? So we'll come back to this one. Let's go on to C. Aircraft and marine navigation systems that incorporate wind information. Incorporate wind information. So we're talking about navigation systems for aircraft and marine vessels. And the navigation systems incorporate wind information. I'd say that's performance via prediction, right? Because, like, wind information, that's like weather forecasting. And that's like prediction, right? That's my mental process there. Like, wind, weather, forecast, prediction. That's the chain of thought there. So I'm pretty sure that one's performance via prediction. Let's go on to the next one. Express elevators in buildings. Express elevators in buildings. So, like, what do they mean by express? Like, are we saying there are like multiple kinds of elevators in this supposed building? I'm thinking maybe this is like performance via parallelism or something along those lines. Let's check the next one. Library reserve desk. So when you say library, the thing that springs to my mind is like caching. Hierarchy of memories? Or could it be... So, library reserve desk. See, I don't go to libraries either. A library reserve desk. So, like, are you saying that you go to the desk at the library to reserve a book? Because like I think of like, you know, a library, you go to the desk, you know, you check out a book, right? But or you go to the desk and you return a book, or you know, things like that. But they say reserve desk. Like I've never thought about like the concept of reserving something in a library. Uh, so I don't know what they're going for there. Um, Again, we'll probably come back to it. Increasing the gate area on a CMOS transistor to decrease its switching time. Well, that one, like, see, that one's clearly Moore's Law. Because, like, that's what I was thinking when I was reading this question. Like, how do you map Moore's Law to something else outside of, like, the computer industry? Because, like, there's not an equivalent. That's, like, a very specific trend that happened in the computer industry. Um, and it seems like they didn't even try to map it to something else. They were just like, you know, yeah, here's Moore's Law. That's an option in there. Um, so let's go on to G, adding electromagnetic aircraft catapults. Allowed by the increased power generation offered by the new reactor technology. I have no idea what they're talking about here. Electromagnetic aircraft catapults, which are electrically powered as opposed to the current steam-powered models. Allowed by the increased power generation offered by the new reactor technology. What? um, you know what express elevators in buildings are? They make the common case fast, right? You put an express elevator, like they're saying, the common case is you want to, you know, go to these certain floors, like the express elevator. This is the common case, and we're making it fast by putting the elevator there, right? Like, because an elevator is much faster than going up the stairs or something, you know, something to that effect. I'm guessing that's what they're going for with the elevator one. So let's think about this electromagnetic aircraft catapult nonsense. Yeah, I don't even know what they're talking about. Uh, we'll probably look that up. So, building the last one here, building self driving cars whose control systems partially rely on existing sensor systems already installed into the base vehicle. Okay, so that's the redundancy. That's dependability via redundancy, definitely. Right. So I think we've got that one down. So maybe I should write these out so we remember what we've got to work with here. Okay, so let me see here. So we've got A, B, C, D, E, F, G, H. Okay, and then let me do like a grid here. So we need to write down the 8 ideas. So Moore's Law is one of them. Abstraction. What else? Common case. Let's see here. So parallelism, pipelining, prediction. Kind of want to scrunch it all to fit on the screen here. Parallelism, pipelining, prediction, memory hierarchies. What else? Is that all of them? 3, 4, 5, 6, 7. Must be one more. Oh yeah, redundancy. Okay, so we're going to kind of check off which ones we think each one might be. And in that fashion, we'll solve it by elimination. Process of elimination. It's like those puzzle games they'd give you in like elementary school. Where like, you know, Todd is 7 years older than Anne, who's 5 years younger than Kelly, and so on and so forth. And then you know, put it all in the table and use the information to kind of figure it out by elimination. All right, so assembly lines in automobile manufacturing, I said that's got to be pipelining, and I still think strongly that's pipelining. So suspension bridge cables. So the elevator one. The elevator one was D. And I think that's the common case fast. So I'm going to tentatively put an X there. F was the CMOS transistor, increasing the gate area and decreasing its switching time. So that's got to be Moore's law. Let's see, that was F. And then H, the self-driving cars one, using the different sensors that were available, that's got to be redundancy, dependability via redundancy. So then, you know, let me just make this clearer by crossing out what we think these can't be, right? So I'm pretty sure, you know, these ones are none of these. And then, of course, these can't be any of these. So I know this is one hell of a mess I've created here, but so like abstraction we see is down to being either B, C, it can still be E, it can still be G, so let's think about this. Use abstraction to simplify design. Suspension bridge cables, aircraft and marine navigation systems that incorporate wind information. Oh, that's the one that we thought was prediction. What was that? C. So C, I think, is prediction. Prediction. So then we can cross this stuff out. Okay, so... Oh, and then we can cross this stuff out. So like this is... Let me circle what we're thinking so far. Just to make it a little clearer. So I think we've got 5 of them here. So abstraction is going to either be B, E, or G. So we're trying to use abstraction to simplify design. I can see how that could be B. What about E, the library reserve desk? We should maybe look up what a library reserve desk means. I think we need to look that up. G, and oh yeah, G, I have no idea what that is. Adding electromagnetic aircraft catapults. So, okay, we're going to look up 2 things here to better understand what they're talking about. First of all, we're going to look up the simple one, a library reserve desk. So, library reserve desk. So reference desk, but is that what they mean by library reserve? Excuse me, by library reserve desk? Support desks. Okay, so this must be a thing that's common at universities, because when we search library reserve desk on Google, we see university, college. So this is like a college thing. That's why I don't understand it. I was like, what the heck is a library reserve desk? Like, I was thinking it was like just like a normal library desk, like if you go to like a public library, or like when you're in like elementary school or high school or, you know, something like that, and there's the school library. There was no concept of reserve desk. And of course, I never went to college, so I was never exposed to this. But apparently, this is a thing. So let's see what it says about it. So this is some university website, reserve desk, located next to the circulation desk on the first floor. The reserve desk contains books and materials placed there by faculty members and graduate teaching assistants for the use of their students. These may include books from the library collection, personal copies of books, photocopies of articles and parts of books within copyright law, course notes and sample exams, and other items. Copies of previous course examinations are also available here, as well as the university budget. Materials are arranged by course name and number and are loaned within a certain time period, usually 2 hours. Valid university ID cards are required to access these materials. Okay, so that's a pretty good description of what a reserve desk is. Let's see a few more. So this is a different college. At the reserve desk, you can check out books, videos, DVDs, and articles placed on reserve by an instructor for a particular class. E-reserves are available. In addition to articles, instructors can post sound recordings and videos as well as links to full text articles, websites, blah blah blah. So when we say course reserves, they mean like things that are specific to classes. So like if you're taking a certain class, you can go to the reserve desk and get materials at the library that's specific to that class, is my understanding. So it's not like for anyone at the university to use. It's for people that need material for a specific class. So like items that professors have assigned to an entire class. So the library's copy or the professor's personal copy is then placed at the desk on reserve for the class so that the material can be available to all the class members. Okay, so I think we understand what they mean by a library reserve desk now. So let's review. With that in mind, how does that fit into what we have here? So is that a form of simplifying design by abstraction? I don't think so. It doesn't seem like parallelism to me. Hierarchy of memory? I mean, it doesn't seem like hierarchy of memory to me either. Well, I guess you could kind of say it's a hierarchy. Like, it's like a cache, a cache of material for a specific class, so to speak. I feel like this one's kind of a stretch to call it any of these big ideas. I mean, we could maybe say it's like redundancy if there are other like materials, like if the materials that are at the reserve desk are also available outside of the reserve desk, you could say it's like redundancy. You could maybe even say it's like making the common case fast. of like, the class members can go to the reserve desk. They don't have to wade through the entire library or whatever. You know, it's like the stuff they need is there at the reserve desk or something. I don't know. Yeah, I don't know. That feels like a stretch to me. That one just, it doesn't really stand out to me as fitting into these categories. So let's look up electromagnetic aircraft catapults. Aircraft catapult. So what is an aircraft catapult? It's a device used to launch aircraft from ships. Okay. It's a form of assisted takeoff. So they actually catapult planes into the air. I didn't know that was the thing. I did not realize that. I mean, I guess I've seen, depictions of this kind of thing now that I think about it. But yeah, I've never thought about that of like, I guess, like I say, you think of depictions of like, like a fighter jet, um, being catapulted off a plane. Like, I think of like like a metal rod and then like here's the plane and it's like, you know, like I think of, I'm pretty sure I've seen depictions of that kind of thing. So I guess aircraft catapult, like this is a thing apparently. I did not know that this is a thing that people do. So they're talking about the electromagnetic one as opposed to the steam one. So here we see steam catapult. And then here we see the electromagnetic aircraft launch system. This is what they're talking about in the book. So, I mean, it's just an all around, like, a better design. And it uses solid state components. I'm kind of reminded of Moore's Law with this, actually. But, uh, like, it's not really Moore's Law in the sense of, the exponential increase in performance of computer systems, or like the shrinking of transistors um, continually over time. Like this is just like one technological advancement over an older technology that's but it's accomplishing the same thing. It's catapulting aircraft into the air. uh, so would you say it's abstraction? Like I guess it simplifies design, Or, I mean, maybe it's not really a simpler design. It sounds pretty complicated, right? But it requires less maintenance because it's solid state. So again, let's think about each one that it could be. Um, Parallelism. I don't see how that's parallelism. I also don't see how that would be hierarchy of memory. It's not redundancy. So I wouldn't say it's prediction. I wouldn't say it's pipelining. I wouldn't say it's make the common case fast. Kind of like the thing that makes me think the most of is Moore's law. Because Moore's law is all about like improving technology. Like that's the closest I can relate this to this, because this is just like improving technology where you're having this as an improvement over the older Steam version. That's the best I can come up with. I don't know. I mean, like, yeah, that maybe it isn't a unique one for each. I guess it didn't say that it's going to be a unique one for each. Or maybe increasing the gate area on a CMOS transistor to decrease its switching time isn't meant to be Moore's law. I mean, they're saying decrease the switching time of the transistor, so you could say that's the common case of what a transistor does. I mean, it's the only thing a transistor does. That I don't know, but you're making the common case fast. That's technically true. Uh, Maybe I'm being led astray here, but I really feel like because there's 8 of these and there's 8 of these, like you'd think they'd have one for each. You'd really think that, right? I really think that, but relating these things to the 8 key ideas is it's not easy to me. I'm not seeing clear like correlations. I can't tell what the authors are going for here. Yeah, I really don't know. Like, the best thing I can say is, like, for B, the suspension bridge one, um, that makes me think, like, the closest I can think of for that was either redundancy, and I think H is redundancy. So I feel like simplifying abstraction to simplify design, like, that's the closest thing I can think of. I mean, you could say that the suspension cables are parallel to each other, but that's not performance via parallelism, in my mind. It's not hierarchy of memory. Like, I think it's like this. That this is this one. So then it's down to, we still need to do parallelism and hierarchy of memories. And they're either E or G. G is the electromagnetic aircraft catapults. E is the library reserve desk. So, library reserve desk. Is that parallelism or is it hierarchy of memory? I feel like it could be hierarchy of memory. Because, like I say, it's kind of, you can kind of say it's like a cache, right? Uh, like, that's the best I've got. I think E, the closest I can come up with, is hierarchy of memory, which means that G would be parallelism. And I guess the rationalization there is if you have a lot of these catapults or something, like, I mean, I guess if you have like an aircraft carrier, you'd probably have a number of these catapults, wouldn't you? Like, if you have a fleet of fighter jets on your aircraft carrier, wouldn't you want like a bunch of them to like launch the entire fleet into the air at once or something? Like, I have no idea, but that's the best I've got. So those are going to be my answers. I'm going to leave it at this. This is what I'm calling for the answers on this one. I definitely don't feel sure about this, so I'd love to see other, like, people who watch this episode. I would love to see your commentary on what you think the answers are for these. So remember, go to forum.risky.tv, and there's a post about computer organization and design 1.13. That's where to go if you want to give your commentary on this problem. I really would love to see commentary for other people, because this one was definitely a stretch for me to try to figure out. I did not see like a very clear correspondence. I was thinking this was going to be like, oh, this is going to be a really easy problem, right? And then it turned out like these really seem like a pretty big stretch to make comparisons. Like, I feel like I understand the 8 big ideas. I don't feel like I'm missing something there. Like, it's not like I'm not getting that. And then, like, I definitely wasn't as sure about a lot of the things that we're trying to compare them to. But I looked them up on Wikipedia, and now I feel like I understand what all those things are, right? Like, I understand the reserve desk, the electromagnetic aircraft catapult, like, that catapults an aircraft carrier. You know, it's on an aircraft carrier. It catapults some form of aircraft into the air, and it's an improvement over the previous steam-powered version. Like, I get that. But how do you relate that to the 8 big ideas? I don't know. So, like I say, I really want to see what you guys have to say, what you guys think about those. But I'm going to move on. So, that was supposedly 5. So they thought that was supposed to be an easy one, I guess. But I did not find that one easy. I don't know. Maybe I'm just missing something, but that one did not seem straightforward to me. So 1.3. Describe the steps that transform a program written in a high-level language such as C into a representation that is directly executed by a computer processor. That's pretty straightforward. It goes through a compiler, and it goes through a linker. So the compiler, the way it works, you have a compiler. It parses the source files. There's in C, we have the stupid C preprocessor, so it needs to do preprocessing actually. So there's the preprocessing. It parses everything, tokenizes, everything into. It builds up the abstract syntax tree. There's of course optimization that gets done by the compiler, and it generates the machine code. Not a completed executable, but it generates machine code that goes into object files. And the object files get linked together by a linker, which also does link time optimization, potentially. And that produces the final executable. That's how that works. I think that's a good explanation there on how the steps go that transform a program into a language like C to an executable. And of course, it's different if we're going to talk about languages like Java, where you have a JIT. And that's an interesting concept. Like, first of all, going simpler, you have interpreters. So, like, say you have a Python interpreter. I don't know if they do JITting these days or whatever, but say they have a naive interpreter, right? In that case, you have an executable file that's already made, the Python interpreter, which goes through the process I just described for C. And then the interpreter takes the source code, it reads it, and then it executes instructions based on what the source code said. That's the idea of an interpreter, right? And the idea of a JIT is, well, you can take the source code and you can compile it at runtime, into a bytecode representation, and then your interpreter can be written like an emulator for a virtual CPU that has this bytecode as its instruction set architecture. And now with JITting, what you do is you say, well, what if that intermediate representation, that bytecode, what if that it happens to be the same, instruction set architecture as the machine you're running on? Then you could actually compile the code down into the machine code for the actual, processor you're running on, and then, put that into memory that's executable, and then just jump the instruction pointer there and actually execute those instructions. That's the idea of a JIT, right? Just-in-time compilation, So those are a few examples of ways you take a high-level language and actually get, instructions that are executable by the machine. Those are some examples of how that is done. And we're definitely going to be diving into that into a lot more detail later in the Risky Business series. And I want to read the LCC book on this series as well, the book club series. But obviously right now we're going through a different book. And there are other books that I want to read as well, so I don't know when we're going to get to that, but it's on the roadmap. 1.4. Assume a color display using 8 bits for each of the primary colors, red, green, and blue, per pixel, and a frame size of 1280 by 1024. There's two sub-questions here. The first one is, what is the minimum size in bytes of the frame buffer to store a frame? The next one is, how long would it take, at a minimum, for the frame to be sent over a 100 megabit per second network? Okay, so there's 1280 by 1024 pixels, and a frame is going to be 1280 by 1024 times, however many bytes are in your RGB representation here. So we have 8 bits per red, green, and blue channels. So that's going to be 3 bytes per pixel, right? So you're saying 1280 times 1024 times 3 would give you the number of bytes in a frame. So, and I don't know if you guys have seen, but I'm working on a calculator. So this is one thing I've been doing a lot. Maybe I should be spending more time doing risky business, but I've been missing actually doing real programming. So I've been doing this. So Pale Moon isn't going to play it, I guess, but I got text input working. I've done a lot more since this tweet. The input scrolling works. It has a cursor. It has normal mode, visual mode, and insert mode. And I'm working on the VI controls right now for this thing. But I'll probably post more on Twitter soon about it. Let me see if I can just open up a Chrome window here. Put that on screen for you guys. Okay, I have this on a thing, don't I? Twitter.risky.tv should take me there. So here you should be able to see the little video here. So this is still a work in progress, but you see here I was demoing that I had the text input working, and like I say, now it's even further than this. It has when you get to the end over here, it'll actually scroll it. I implemented it the same way that WeChat does it, and it has, like I say, it has a cursor. It has multiple modes Vim style. But yeah, this is something I've been working on. And if you go to blog.risky.tv, I talked about the design of this program, what it's going to be. I'm not going to go over everything right now, but in the July overview, I talked about it here. So, and you can see this is the real explanation down here. I talked about it on IRC, on the handmade-network IRC, and I posted the logs here for you guys to read if you're interested in what I'm doing on the pcalc thing. And this is going to be available to $5 backers on Patreon. So when this program is shippable, those people will be getting it. So it's something to keep an eye out for. The reason I just mentioned that right now was because we're about to do some calculations, and it would be nice if that program was ready to use, because I already want to use it rather than this, but it's not there yet. So we're going to use Google. So we're going to do 1024 by 10, what was it? Or 1280 by 1024. Well, order doesn't matter in multiplication. So 1024 by 1280 by 3. why did, oh, this, sorry, it needs the star, the asterisk, not the X. Okay, so this number here is the number of bytes. That's the answer to A, the first part of this question. Okay, so yeah, that looks correct. 1280 by 1024, 3 channels, 8 bits each, so those many bytes. Seems right to me. How long would it take at a minimum for the frame to be sent over a 100 megabit per second network? So so if we say here, let me copy this value here. Okay, so 100 megabit, can it do that? Probably wants it like this. There's megabits. And this is megabit, not mebabit, right? That we're talking about. So so yeah, this is megabits. If it was mebabits, they would use the I, the lowercase I after the M for a megabit. So yeah. So this is how many bits per second, but we want that in bytes. So megabytes per second would be 12.5. So then if you say this number divided by 12.5 megabytes per second, so I get this number of seconds, right? Is that right? So if you have 12.5 m over s, right, per, megabits per second, right? And you're saying, so we're going to say this is like 12.5 over 1 second, right? And how does this compare to if we say we have 1024 by 1280 by 3 bytes? Well, first of all, let's convert that into the same unit. So this number, is that the right number? This number times our bytes to megabytes. So this is how many megabytes you have, right? So let's say equals 3.9 megabyte over how many seconds? X seconds, right? So then you say 3.9 times 1 and then divide by the 12.5 to get X. So 3.9 blah 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 divided by 12.5 equals seconds. So if we take this number divided by 12.5, so it'll take 0.3145728 seconds. So like about a third of a second. Like a third would be 0.33 repeating, right? So that is, I believe, the answer there. And again, if I made any mistakes in my math, let me know on the forum post right here. So let's move on to the next one. Consider 3 different processors, P1, P2, and P3, executing the same instruction set. P1 has a 3 GHz clock rate and a CPI of 1.5. P2 has a 2.5 GHz clock rate and a CPI of 1.0. P3 has a 4.0 GHz clock rate and has a CPI of 2.2. Which processor has the highest performance expressed in instructions per second? Then they ask, if the processors each execute a program in 10 seconds, find the number of cycles and the number of instructions. And then finally they ask, we are trying to reduce the execution time by 30%, but this leads to an increase of 20% in the CPI. What clock rate should we have to get this time reduction? Okay, so first of all, which processor has the highest performance expressed in instructions per second? So P1 was 3 GHz and a CPI of 1.5. P2 was 2.5 GHz and a CPI of 1. P3 was 4 GHz and a CPI of 2.2. So let me go back to Milton here, and we have those performance equations we wrote down. Okay. So they want to know instructions per second. Which processor has the highest performance expressed in instructions per second? So, I mean, they gave us the CPI and the clock rate. So the clock rate is like a hertz is how many cycles per second. So if it's like 60 hertz, you're saying 60 cycles per second, or like, 60 frames per second, because that's, like display speed. But like that's how we're going to get seconds into the equation. It's based on the clock rate. But then CPI. So CPI is like the average clock cycles per instruction. So really what we're talking about is CPU time, this equation right here. CPU time is equal to instruction count times CPI over clock rate, right? But we don't have an instruction count. But I guess it doesn't really matter in this case, does it? So like if we just take the CPI divided by the clock rate, that would basically give us what we want, right? I mean, well, I mean CPI over clock rate, like let's think about the units here. So clock cycles per instruction. So that's saying cycles over instruction. And then we're saying divide that by clock rate, which in these examples we're talking gigahertz, but if we want seconds, we want hertz. So that's not exactly the unit we're looking for, is it? Like we're trying to solve for the unit instruction over seconds, basically. So let me see here. So like hertz is cycle per second would be the units, right? So let me go over here. So we say we have sorry, that's supposed to be an I, not a Z. Let me rewrite that. Okay, CPI is equal to cycles per instruction. And the goal is to get instructions per second. So we need something that relates hertz to CPI. We need an equation that uses hertz and CPI, right? Because like you can't rewrite one into the other one, so to speak. They're independent. So yeah, we come back to CPU time is equal to instruction count times CPI divided by clock rate. So I feel like that's probably as good as we're gonna get. So if we're saying, so instructions times CPI over clock rate, so instructions times CPI over hertz would be clock rate. And then we replace CPI with cycles per instruction. So we say instructions times cycles per instruction. And then that is all over cycles per second. And then it's a question of simplification here. So I believe we could put these seconds from down here on the top up here. So like it'd be instructions times cycles per instruction times seconds over cycles or something like that, right? Let me just double check that on Wolfram Alpha. That's not what I wanted. Okay, so we're going to say n times C over I divided by C over S. Let me stick some more parentheses in there just to be extra confident there. So yeah, this is what we're doing here. And it says it simplifies to negative I and S. So the cycles cancel out. So we get negative instruction times instructions times seconds So that seems like nonsense to me. Like, I mean, we don't have an equation here, first of all. Like, there's not like there's not an equality, and like, what does negative instruction time instructions times seconds even mean, right? Well, I mean, the equality that we were looking at was CPU time is equal to this. So it would be CPU time equals this, CPU time equals this. But I mean, we're not getting to instructions per second here. Sorry about that. Like we're not getting to instructions per second this way. So maybe I'm just thinking about this in a stupid way. Like, I mean, let's just go back to thinking about Hertz and CPI. So they both use cycles, right? And we know that cycles is going to be the same. So, I mean, if we flip CPI around and say instructions per cycle, and then cycles per second, you could get instructions per second, right? So like IPC, instructions per second, or per cycle, is equal to the inverse of CPI, and that's the unit instruction per cycle. And then we say we have the hertz, the cycles per second. So like if we said instructions per cycle times cycles per second, wouldn't the cycles cancel and you get instructions per second? So I'm pretty sure what we want to do here is take the inverse of the CPI in each case and then multiply that by the hertz. Okay, so let's write out the processors. P1 equals 3 gigahertz. And a CPI of 1.I. 1.5. P2 equals 2.5 gigahertz. CPI of 1. P3 is 4 gigahertz. CPI equals 2.2. All right, now we need the inverses of each of these CPI values. So 1 over 1.5, 1 over 1, 1 over 2.2 would give you the IPC. So let's start with P2 because the IPC is just going to be 1, right? So we're saying 1 times 2.5 equals 2.5. So the instructions per gigasecond is 2.5. Like the giga in gigahertz, like that's just a constant factor. That's times 10 to the power or something, right? So we can just ignore that. Like we don't care about converting from gigahertz to hertz. It really doesn't matter. It matters if like P1 is gigahertz and P2 is megahertz and P3 is hertz. Like then you need to convert them to a common unit. But these are all gigahertz, so we can just like we don't care about actually getting it down to hertz. So this one's just 2.5. And then P3 is going to be 4 times 1 over 2.2. Let's go back to Google. 1 over 2.2. .45 repeating. So we're going to take that times 4 gigahertz. And that gives us 1.81 repeating. So to summarize, this one's 2.5, this one's 1.81 repeating. And then let's do 3 times 1 over 1.5. Is 2. All right, so we've got our values for instructions per second. It's not actually the proper unit because I didn't convert from gigahertz to hertz, but the relative values are correct, right? They're just like you shift the decimal place, so that's not important. So which processor has the highest performance expressed in instructions per second? I would say that it's processor 2 because it had 2.5 instructions per second by some, like multiplied by some constant factor, right? Whereas the other ones were 2 and 1.81. So yeah, I would consider the processor 2 to be the fastest. And intuitively, if you think about it, like cycles per instruction, if the value 1.5 is saying that, it takes 1.5 cycle for every instruction that you run. So it's running at 3 gigahertz, but, we're only doing one instruction every 1.5 of those cycles. So you see how you get 2, right? Because like 1.5 times 2, you get the 3. And for this one, right, it's just one CPI, so it's just the 2.5. For this one, it's the 2.2, and you got the 4 gigahertz, right? You see how you get the 1.81 there in the same way as 2.2 times 1.81. That's gonna give you the 4. Like I say, the intuitive thought process here is that there's 2.2 cycles for every instruction. You're running at 4 gigahertz, which is faster than the other two processors, but because it takes you so long to actually execute an instruction, if it took you 2 cycles per instruction, then you're like running at half the actual speed, right? You're running at 4 gigahertz, but you're only doing 2 gigahertz worth of instructions. But you're doing 2.2, so it's even worse than that. It's even lower than 2 intuitively. And you see, in fact, that is the case. It's 1.81 repeating, according to the math that I did. So that's my answer to that one. Okay, if the processors each execute a program in 10 seconds, find the number of cycles and the number of instructions. Okay, so that should be pretty straightforward from what we've already done. So we're saying for each processor, it takes 10 seconds to execute this mystery program. And so we want to know the number of cycles and the number of instructions, right? Yeah, the number of cycles and the number of instructions. So processor 1, we know it takes two like not instructions per second, but so this is the case where it would actually have helped to do the constant factor, because then we could just use these values, but my values are off by a constant factor. So we could look up the constant factor, but let's work through it the hard way instead. So we're saying it takes 10 seconds So if we have 3 gigahertz, let's convert that into hertz. So I guess Google doesn't do hertz, but a gigahertz is this many hertz or something, or okay, this many hertz is 1 gigahertz is what they're saying. So this number times 3. So that's how many cycles run in a second. right? And we're saying the program took 10 seconds to run. So this number times 10 is the number of cycles. So my answer is this many cycles. That's a lot of cycles. And then we know the CPI. So there's 1.5 cycle per instruction. So again, if you flip that to 1 over 1.5 instructions per cycle, right? So we're saying let me do the algebra here. So we have cycles per instruction, and we have 3 times 10 to the n. I didn't count how many zeros there are, so I'm just going to say n cycles. And a 3 gigahertz processor. Like, how do we get this to instructions? My algebra is failing me today. Okay, so 3 times 10 to the n cycles per instruction. Or wait, so we have cycles per instruction equals 1.5. So yeah, I think I'm right that I need to do it as IPC, right? Because if you flip cycles per instruction, then you have instruction per cycle, and then you have these, 3 times 10 to the n cycles. So like what I'm saying is if you multiply these, like this is over cycles and this cancels, right? And you get instructions. So I'm pretty sure it's you take the IPC times the number of cycles, and that'd give you the number of instructions. Like I say, clearly my algebra is failing me today. It's taking me a long time to do basic equalities. But if I am correct, so 1 over 1.5 so first of all, I copied this value, right? Yeah. So times 1 over 1.5. So this many instructions. That's the number I got there. So again, I don't want to bother counting all those zeros. But this is the number of cycles. This is the number of instructions. And again, my viewers, if you want to follow along, I'd love to hear if I did my math wrong or if I got this right. Let me know what values you guys got for the number of cycles and instructions. Okay, so the next one is 2.5 gigahertz. So we're saying 2.5 gigahertz times 10. So it's going to be 2, 5, and a bunch of zeros is the number of cycles. And then times 1 for the IPC. So it's going to be the same number of instructions. So I'm just going to leave it at that. It's 2, 5, and a bunch of zeros, right? 4 gigahertz, and then 2.2. So 1 over 2.2. So then we just say 4 times 1 over 2.2. Oh, and that was the same. So it's like the same values, just with a bunch of zeros at the end. So I mean, it's the same exact values, just times 10, right? I'm pretty sure it's just the same exact value as instructions per second, just times 10, because 10 seconds, right? So that was the long-winded way of doing and that's what I said in the beginning. I was like, well, you just take this value, but if I don't have it in hertz, so you need to multiply it by a constant factor. And that's exactly what we ended up with. And so what I did is I went the long way and redid the algebra, which is good. I mean, it's always good to practice your algebra. I clearly need the practice. So, it's a good homework, but there is obviously a much faster way to do that. But anyway, yeah, I'm pretty sure I got the right answers there. Like I say, let me know if I'm wrong, but those are the answers I got. Now, we are trying to reduce the execution time by 30%, but this leads to an increase of 20% in the CPI. What clock rate should we have to get this time reduction? So they're asking that for all three of them, I guess. Okay, so we are trying to reduce the execution time by 30%. So presumably we're still talking about the 10-second example or something, right? So we have this 10-second program. It has so many cycles, so many instructions. So, I mean, the instruction count isn't going to change, right? So we're going to say the instruction count that we had over here. And again, like I say, constant factor, blah, blah, blah. But, these number of instructions for each processor, we're taking that program, that imaginary program we have that has that many instructions, and we're saying we want to change the clock rate so that we get a 30% time reduction, but we're causing an increase of 20% in the CPI. So first of all, you need to increase the CPI of each one by 20%. So like 20%, we're saying 20 over 100 is 0.2, right? And so if you're increasing it by 20%, you're saying times 1.2 then, right? So this one's, let's start with P2 again, because that's the easy one, right? Since the CPI is just 1. So the CPI in our change is going to be 1.2, but we can set the clock rate to whatever we want, right? And the goal is to get a program that's 30% faster. So that'd be like saying 10 times 0.7, right? So like 7 seconds would be 30% faster than the 10-second program, right? So for these 3 processors, we want the 10-second program to take 7 seconds. This one's going to have a CPI of 1.2. So if you have a CPI of 1.2 and you want the program that uses the 2.5 times 10 to the whatever instructions, how many seconds would you need? You know, I really don't like these problems because they keep making me convert it to hertz, and I don't want to count zeros. That's so boring. Like, what is the point of making me count zeros, man? But, like, I need to know the value in hertz to do this, don't I? Or the proper, like, I need to know how many instructions this is. Can we do it without doing the proper values? Let me think about this. So if I say there's 2.5 instructions that it executes, and we're changing the CPI to 1.2, so I mean, what was the algebra we did to get from 2.5? We did the 2.5 times the IPC, so 1 over the CPI, 1 over 1.2, 2.5 times 1 over 1.2 to get the instructions, and the instructions would actually be times 10, and it was the 1.0, not the 1.2. But then working backwards, we have the 2.5. So if we say 2.5 divided by 1.2, and that might be off by like 10 or something. So like 2.08. But wait. So, but we want to get this 7 seconds. How does that work into this? So like 7 times the gigahertz, whatever that value is going to be, which is the answer, 7 times the answer is the number of cycles times the IPC equals the number of instructions. So we've got the number of instructions, we've got the IPC, we know there's 7 times something here. So 7 times something times 1 over 1.2 equals 2.5. Decimal point might not be right. 7 times 2.5 times 1 over 1.2, or 7 times something. So yeah, here, let me write this out. So we have x times 7 times 1 over 1.2 equals 2.5 fudging the decimal place. So 7 times 1 over 1.2, we can simplify that. So 5.83 repeating. That's this right here. So then if we divide 2.5 by 5.83 repeating, because that's going to cancel this out and give us x, which is the gigahertz. And like I say, I fudged the decimal places because I really don't care. So let's see here, 2.5 divided by 5.83 repeating. So here, let's just do this. 2.5 divided by that gives us 0.428. And like I say, I fudged the decimal place, so it's probably 4.28. So I think it's 4.28 gigahertz is the answer for P2. And like I say, I really did a lot of hand waving because I just don't want to count. I don't want to count zeros, man. It's boring to count zeros, you know. So yeah, I'm saying 4.28 gigahertz for P2. That's my answer. Okay. And like I say, you guys can if you want to count the zeros, or just, you know, look up what power 10 to the power of what is gigahertz, you know, and go from there. You can get a more rigorous answer and inform me of what the proper answer is. Okay, so let's do P1 next. So we're saying 7 times x times, so 1.5, let's see, we said it was 1.5 times 1.2. So here, 1.5 times 1.2, that's what that value is supposed to be. And then, which one are we doing? We're doing this one right here. So the IPC for that one was 2, or the value over there is 2. So 5.1 gigahertz. Again, assuming the decimal place is off, assuming my math is right, and assuming my decimal place is off by 1, because the times 10 from the 10 seconds or whatever, I'm saying it's 5.1 gigahertz for P1. And let's do this last one. So this value should be 2.2, and this value should be 1.81. Repeating, but I'm just going to say 1.81. And what was this one again? 2.2. So this one should be 6.82 gigahertz for this to work out. And I'm not going to double check my math or anything. Like I say, you guys can work through the exercise yourself and see if you get the same answers that I just did. But those are the answers that I got. And I'm going to just go with it because that was boring to me. I don't want to continue that. I'm not going to get a rigorous answer. I like just doing hand waving and saying, yeah, that's probably right. That's the way I approach math. Okay. 1.6. Okay, consider two different implementations of the same instruction set architecture. The instructions can be divided into 4 classes, according to their CPI, classes A, B, C, and D. Okay, so 2 different implementations of the same ISA, and within that ISA, there are 4 different instruction classes that have different CPIs, classes A, B, C, and D. P1 has a clock rate of 2.5 gigahertz and CPIs of 1, 2, 3, and 3, and P2 with a clock rate of 3 gigahertz and CPIs of 2, 2, 2, and 2. Given a program with a dynamic instruction count of 1.0 E6, so 1.0 times 10 to the 6th, instructions divided into classes as follows. 10% class A, 20% class B, 50% class C, and 20% class D. Which is faster, P1 or P2? And then they say, A, what is the global CPI for each implementation? And B, find the clock cycles required in both cases. So wait, find the clock rate required in both cases for what? I don't know if I understand what they're asking there. Because we know the clock rates. P1 is a clock rate of 2.5. P2 is a clock rate of 3. And they're saying find the clock... Oh, the clock cycles required in both cases. Clock cycles, not clock rate. Okay. So, first of all, which is faster, P1 or P2? So our program has 10% class A. So we say 10% times a CPI of 1, so 10%. Class B was 20%. And we have 2 for the CPI of Class B. Okay, so 2 times 20%. So 10%, like that's going to be 0.1 times 1. So 0.1 and then 2 times 0.2, which is 0.4. And then are we doing the average of this to get the global CPI, or are we just like adding them? So 0.1, 0.2, or 0.4, 50% class C, and class C for this processor is 3. So 0.5 times 3, which is going to be like 1.5, right? And then 20% class D, which is 3. So 0.6. So let's just add them up. 1.5 plus 0.6 is going to be 2.1 plus 0.4 is going to be 2.5 plus the 0.1. What did I say? 2.5, 2.6 total? So yeah, it would just be the sum, right? If I did my mental math right, I just did all of that in my head. So if I did that right, I got 2.6 for the first processor for the global CPI. And then for the second processor, we have 2 CPI across the board for all 4 classes. So it's just going to be 10%. So 0.1 times 2 is 0.2. And then 20, so 0.4. So we started with 0.2, so it's 0.6, 50%, so 1, so 1.6, 20%, 4, so 2. Well, that makes sense. The global CPI would be 2 because all the CPIs are 2. So I definitely did the mental math right on that one. Okay. Okay, and then we're saying which is faster, P1 or P2, for running this program. So they also gave us the number of instructions, 1.0 times 10 to the 6th. So we've got the CPI for each instruction count. We've got the global CPI, we just calculated. We know the processor speeds. So let me think about this. I mean, if we want to know which one's faster, we're going back to CPU time, right? I'm pretty sure we're going back to CPU time. So like instruction count, and we're just going to call it 1. It's times 10 to the 6th or whatever. But again, let's just fudge the constant factors and say this is 1 times the CPI. And again, we're going to use the global CPI. So for processor 2, we're saying 1 times 3 divided by clock rates. So it was 3 gigahertz, right? Or wait a minute, it was 1 times 2 divided by the clock rate of 3 gigahertz for the second processor. Yeah, so 2 over 3, 2/3. The CPU time would be, what is that, like 0.66? Pretty sure that's like 0.66. Yeah. And then for the first processor, I guess I did all this in my head, so I don't need to open up Milton. Okay, first processor was, so I probably should have wrote down what I said the global CPI was. I think it was 2.6. P1, let me see here, 2.5 gigahertz. Let me just double check the CPI again. So 1, 2, 3, 3 were the CPIs, and it's 10%, 20%, 50%, 20%. Okay, 0.1 0.4, so 0.5. And then 15% times, so 1.5, so that's 2 total. And then 3 times 20, 6.6, so 2.6, yeah. 2.6 and a clock rate of 2.5 gigahertz. So if we just take CPI divided by, so 2.6 divided by 2.5. So 1.04. So P2 is the faster of the two. And then they say find the clock cycles required in both cases. Well, the clock cycles would be the time it requires times the gigahertz, right? Like times the clock speed. Or would it be divide? Like the value divided by the clock rate. So let me think. What did we just calculate? We calculated CPU time, which time is like seconds, right? So we could say this is seconds. And of course, the constant factor is wildly off, obviously. But 1.04 seconds, some unit of time, and hertz is cycles per second. So yeah, you'd multiply, right? So like 1.04 times 2.5, but isn't that just going to give you the 2.6 back? Like it's probably the CPI times some constant factor or something. 2.6 times, like, okay, 2.5 times 1.04, that gives 2.6, right? Yeah. So I think it would be the same as the CPI times the constant factor. Again, correct me if I'm wrong. I'm probably wrong. I don't know, man. I'm fudging a lot of the math here because it's boring. But I'm going to call that one good enough. We're going to move on to the next. I mean, in fairness, we're going on to we're like 3.5 hours in or something into the stream, right? So, okay, compilers can have a profound impact on the performance of an application. Assume that for a program, compiler A results in a dynamic instruction count of 1.0 times 10 to the 9th and has an execution time of 1.1 second, while compiler B results in a dynamic instruction count of 1.2 times 10 to the 9th and an execution time of 1.5 seconds. Find the average CPI for each program given that the processor has a clock cycle time of 1 nanoseconds. Assume the compiled programs run on 2 different processors. If the execution times on the 2 processors are the same, how much faster is the clock rate, or is the clock of the processor running compiler A's code versus the clock of the processor running compiler's B code. A new compiler is developed that uses only 6.0 times 10 to the 8th instructions and has an average CPI of 1.1. What is the speed up of using this new compiler versus using compiler A or B on the original processor? So again, I just want to fudge it with mental math because this is like really boring homework. So compiler A has an instruction count, and we're just going to call it 1. It's 1 times 10 to the 9th, but we're just going to call it 1. And has an execution time of 1.1 seconds. Find the average CPI. And it says the clock cycle time of the processor for this question A is 1 nanosecond. Okay, so let's go back to our performance equations. So we know the clock rate, we know the cycle time, which is the inverse of the clock rate. Whoops. Okay. So you see that right here. 1 over clock cycle time is the clock rate, right? So we know the clock rate. We know the instruction count. We know the... do we know the CPU time? Let me reread that. We know the CPU time, right? Yeah. So for this one, it's 1 instruction count, 1.1 second time. So we can just do algebra, right? So we're saying clock rate, we said it was 1 nanosecond. So we're going to say clock rate is 1, because 1 over 1 is 1, right? That's the inverse. So 1 is the clock rate, and I'm not bothering with the unit there. Instruction count was 1 times 10 to the 9th. So again, I'm just going to call it 1. CPU time was 1.1. So 1.1 equals CPI, because the 1 over the 1 cancels. So CPU time, CPI equals 1.1. So that's what I get for CPI. I didn't do the units, but 1.1 times some constant factor. 1.1 sounds like a reasonable CPI, so it's probably just 1.1. Okay, now second processor. Second compiler. So second compiler generates an executable that's 1.2 times 10 to the 9th. So we're just going to call it 1.2, and an execution time of 1.5. Okay, so we're saying 1.5 equals 1.2 times CPI over 1. So again, we don't need to worry about the over 1 thing. We're saying, what was it again? 1.5 equals 1.2 times CPI. So 1.5 equals 1.2 times CPI. CPI equals 1.5 over 1.2. I feel like the thing that's probably making me feel so bored with this stuff is that I have to use the stupid Google calculator because I want to go it just makes me want to go work on my calculator, right? I've got a calculator in the works, man. I shouldn't be having to do all this boring homework with Google. Okay, so 1.25. I'm saying that the CPI for compiler 2, 1.25. So that's the CPI for each program, given the processor has a clock cycle of 1 nanosecond. And then we say, assume the compiled programs run on 2 different processors. If the execution times on the 2 processors are the same, how much faster is the clock of the processor running compiler A's code versus the clock of the processor running compiler's B code? That's an interesting one. Okay, so what were the answers that I said? So 1.25 was that one. And then what was the other one? Let me look back here. It was just 1.1, right? I'm pretty sure because it was 1.1 second and we said 1 instruction count, 1 nanosecond time. So yeah, 1.1 and 1.25. And so how much faster does it have to be for them to be the same? So A equals 1.1, and then we're saying B equals 1.1 because we're making it faster, right? But old B, right, goal, old B equals 1.25. So that's when they were running on the same processor, right? So 1.5 times x equals 1.1, right? Can't we just do that? I think you can just do that, can't you? Maybe I'm wrong, but because then you just divide by 1.25 on both sides, right? And that should tell you how much faster it has to be. So 1.1 divided by 1.25. So 0.88. So what does that mean? Does that mean 22% faster or something? I think that would be 22% faster. So again, I'm just doing hand-wavy mental math, but with my very sloppy methods, I have determined that it would be 22%. Or we'd say that compiler A's, the processor running compiler's A code is 22% faster than the clock of the processor running compiler B's code. That would be my answer. Now letter C. A new compiler is developed that uses only 6 times e to the times 10 to the 8th instructions and has an average CPI of 1.1. What is the speedup of using this new compiler versus using compiler A or compiler B on the original processor? So see, if I say it's 6, like doing the normal hand waving I'm doing, this is 10 to the 8th, that one was 10 to the 9th, so we're going to be off by a decimal place. We already know that much, right? If we continue hand waving like I am. So with that in mind, so it has a CPI of 1.1. So let's go back to our equation. So was this a new compiler? Yeah, this was a new compiler, right? Yeah. So we say CPI is going to be 1.1. Instruction count is going to be 6. So 6.6 times 10 to the 8th over clock rate. And we were hand waving and saying the clock rate is 1 because it's 1 nanosecond per clock cycle. Like a clock cycle is 1 nanosecond. So 6.6 equals CPU time. Or it would be 0.66. So they're saying, what is the speed up using this new compiler versus using compiler A or B on the original processor? So the original processor, it was 1.1 second and 1.5 second for the two compilers. And we're saying this is going to be 0.66 seconds. So what is the speed up of 0.66 compared to 1.1, first of all? So what we do like 1.1 times something equals 6.666 or 0.66. Like let's just do 1.1 divided by 0.66. So the question was, what is the speed up? So compared to compiler A, I'd say it's like 1.6 times faster or something. And then, or I guess here, let's flip this. Because before we were talking in percents. I don't think that looks like a percent. So 0.6. So it's like 40% faster, right? I think it's 40% speed up over compiler A. And compiler compiler B was 1.5. So like a 66% speed up compared to compiler B. So those are my answers. My really bad mental math, fudging constants, Google calculator calculations. And like I say, if you guys do it more rigorously, you can discuss on the forums here. And I'd love to see some discussion about that kind of thing. Let's move on to the next question. 1.8. The Pentium 4 Prescott processor, released in 2004, had a clock rate of 3.6 gigahertz and a voltage of 1.25 volts. Assume that on average it consumed 10 watts of static power and 90 watts of dynamic power. The Core i5 Ivy Bridge, released in 2012, has a clock rate of 3.4 gigahertz and a voltage of 0.9 volts. Assume that, on average, it consumed 30 watts of static power and 40 watts of dynamic power. Okay. 1.8.1. For each processor, find the average capacitive loads. Okay, so we briefly saw the power equations. Okay. So what was the symbol again? I think it meant proportional to. Like energy is proportional to capacitive load times voltage squared. Single transition 1/2 times capacitive. I wrote capacitive, but I think it's actually just capacitive is the word we're looking for here. Yeah, in here it says capacitive, C-A-P-A-C-I-T-I-V-E. I think that's the word I meant when I wrote capacitive here. So capacitive load. So we're finding the average capacitive loads for each processor. So do we know the energy and the voltage squared? But I mean, it's not inequality, it's a proportion, right? How do you find the capacitive load if you have a proportion? We know the clock rates, the voltage, and how much energy it consumed, right? So like the first one consumed 100 watts if you just add the static and dynamic together. So 100 proportional to something times voltage squared, where voltage was 1.25. So let's just assume you can do it as an equality. I don't know if that's correct or not, but let's just assume you can do it as an equality. So if we say 100 is equal to something times 1.25 and then square it, so 1.25 squared, so 100 divided by 1.25 squared. So we shouldn't need the parentheses, but I don't know if this will properly do order of operations there. So it gives us 64. And again, I don't know if you can do that when it's not a proper equality. But I'm gonna say 64. Like, I don't know, man. I've never done this kind of math before. So I'm just gonna say the average capacitive load for the Pentium 4 Prescott is 64. Whatever the I don't know what the unit of capacitive load is, but 64 of that unit, I guess. I don't know. And then Core i5, so it has 0.9 voltage and 30 plus 40 watts, so 70 watts divided by 0.9 squared. So 86.4 blah blah blah. That's what I got for that. Find the percentage of the total dissipated power comprised by static power and the ratio of static power to dynamic power for each technology. Percentage of total dissipated power. What does that mean? Percentage of total dissipated power. Well, power is equal to or proportional to single transition times frequency switched, right? So if you take a single transition, 1/2 times the capacitive load times voltage squared, and then say times the frequency of the processor, would that give you the power? But then it's saying the percentage comprised by static power. Or wait, I was an hour off, wasn't I? It's only been 3 hours that we've been streaming? Okay. See, the problem here is my lack of a background in like electrical circuits and that kind of thing. So I don't remember this talking about like static and dynamic power. I'm not sure I'm following what they're asking here. So I'm looking in the book on the chapter on power 1.7 just to get a review here. So we see the equations we were looking at. Oh wait, here in the elaboration at the end of the chapter, there's two elaborations. Here they're talking about this stuff. So elaboration, although dynamic energy is the primary source of energy consumption in CMOS, static energy consumption occurs because of leakage current that flows even when a transistor is off. In servers, leakage is typically responsible for 40% of the energy consumption. Thus, increasing the number of transistors increases power dissipation. Even if the transistors are always off, a variety of design techniques and technology innovations are being deployed to control leakage, but it's hard to lower voltage further. But it doesn't talk about like how you calculate the static versus the dynamic energy. Like, is it just the same equation, but you don't use the sum of the two? I don't know if I follow. So I want to do a little bit of Wikipedia searching here to get a better background on this stuff. So first of all, average capacitive load. Like, what's the unit of that? So power factor. It's a dimensionless number. So it doesn't have a unit? So yeah, the capacitive load doesn't have a unit apparently. It says they're in the closed interval of -1 to 1. I thought I got numbers a lot larger than that, like 64 and stuff. Maybe I had the units off, like the decimal place off. Maybe it was like 0.64. Since I'm fudging numbers, that's probably the case. So like static power versus dynamic power is the other thing that I'm wondering about. So I understand that the static power is like the power that's leaking, right? Or like the power that's needed just to run the thing without actually like doing work. Whereas like dynamic power depends on the load, right? But I don't think Wikipedia has like pages about this. So I want to know like percentage total dissipated power comprised of static power. solutions, computer organization and design. Computer organization design solutions.blogspot.com. That doesn't sound like a very legit thing, but I mean, hey, if they've got answers, might as well take a look, right? I mean, that looks sketchy. Links, get exercise solution. Yeah, I don't know about that, man. Like, I just want to understand what they're even asking, is the thing. So, I don't even know what to search for. Total dissipated power. So let's just click this first thing and see what it has to say. Basics, power dissipation, and electronic components. An ever-present challenge in electronic circuit design is selecting suitable components that not only perform their intended task, but will also survive under foreseeable operating conditions. A big part of that process is making sure that your components will stay within their safe operating limits in terms of current, voltage, and power. Of those three, the power portion is often the most difficult for both newcomers and experts because the safe operating area can depend so strongly on particulars of the situation. Okay, starting simple. This sounds like my kind of thing. I need to start simple here. Let's begin with one of the simplest circuits imaginable, a battery hooked up to a single resistor. Okay, I'm following you so far. So we've got a battery, it's a 9 volt. We've got a resistor, a 100 ohm resistor here. So it says here we have a single 9 volt battery and a single 100 ohm resistor hooked up with wires to form a complete circuit. Easy enough, right? Yes. But now, a question. If you want to actually build the circuit, how big of a 100 ohm resistor do you need to use to make sure that it doesn't overheat? That is to say, can we just use a regular 1/4 W resistor? Is that 1/4 watt resistor? Like, I thought we were talking about size. What is the, I don't I don't even know, man. Like the one shown below, or do we need to go bigger? So here's a picture of a resistor. Okay, to find out, we need to be able to calculate the amount of power that the resistor will dissipate. Right, here's the general rule for calculating power dissipation. Power rule, P equals I times V. If a current I flows through a given element in your circuit, losing voltage V in the process, then the power dissipated by the circuit element is the product of the current and voltage. How can current times voltage end up giving us a power measurement? To understand this, we need to remember what current and voltage physically represent. Electric current is the rate of flow of electric charge through the circuit, normally expressed in amperes, where 1 ampere equals 1 coulomb per second. The coulomb is the SI unit of electric charge. So I mean, current is just rate of flow. That's how fast it's flowing. So current equals speed, basically. Voltage, or more formally electric potential, is the potential energy per unit of electric charge across the circuit element in question. In most cases, you can think of this as the amount of energy that is used up in the element per unit of charge that passes through. Electric potential is normally measured in volts, where 1 volt equals 1 joule per coulomb. The joule is the SI unit of energy. So they're saying that we should think of voltage as how much energy a electric component is going to consume. That's how they're describing it to us. So if we take a current times a voltage, that gives us the amount of energy that is used up in the element per unit of charge times the number of those units of charge passing through the element per second. So 1 ampere times 1 volt equals 1 coulomb per second times 1 joule per coulomb equals 1 joule per second. Right. The resulting quantity is in units of 1 joule per second, a rate of flow of energy better known as power. The SI unit of power is the watt, where 1 watt equals 1 joule per second. Okay, so it gives us watts. So 1 ampere times 1 volt equals 1 watt. Okay, so I mean we have a 9 volt battery in this example. Okay, back to our circuit. So to use the power rule, P equals I times V, we need to know both the current through the resistor and the voltage across the resistor. First we use Ohm's law, V equals I times R, to find the current through the resistor. So they're saying to use the power rule, P equals I times V, we need to know the current, which is the I in that equation, and the voltage across the resistor, So it says you use Ohm's law, V equals I times R, to find the current through the resistor. So, okay, so the voltage across the resistor is V equals 9 volts because we're using a 9 volt battery, right? So then the resistance is 100 ohms. So we're saying 9 times something, or 9 equals something times 100. So 9 over 100 equals I, right? And that's 90 milliamps or whatever. Milliamperes or something. Is that what amp stands for? Like, I thought amp was like a different unit, but maybe it's just a shorthand for amperes. I don't know. Therefore, the current through the resistor is I equals V over R equal, yeah, so that's what I just said. Then we can use the power rule, P equals I times V, to find the power dissipated by the resistor. The current through the resistor is the 90 milliamps or whatever that we just calculated. The voltage across the resistor is the 9 volts. Therefore, the power dissipated in the resistor is the 90 times the 9 volts. And you get this 0.8 watts, apparently. So that's the point. That's saying it's 0.81 watts dissipated by the resistor. So then they say, can you go ahead and use that 1 over 4, and I guess that means watt, but I don't see how that relates to the size of the thing. 1 over 4 watt resistor? No, because it would likely fail from overheating. The 100 ohm resistor in the circuit needs to be rated for at least 0.81 watts. So I think when they say 1 over 4 W, I think what they're saying is 0.25 watt resistor. And it needs to be rated for at least 0.81. So generally one picks the next larger available size, so 1 watt in this case. Here's a picture. Because a 1 watt resistor is much larger physically, it should be able to handle dissipating a higher amount of power with its higher surface area and wider leads. It may still get very hot to the touch, but it should not get hot enough that it fails. So I'm getting an understanding of like power dissipation, but I still don't understand like static versus dynamic. Like, I don't see how that factors into it yet. So here we have for 25 ohm resistors. So you're still getting the same resistance total, but you're spreading it out across these 4 different resistors, and they're each the 0.25 watt kind. So it says there's only 1/4 as much voltage across each resistor. There's only 1/4 as much power dissipated in each resistor. So one only needs the 4 resistors to be rated for 1/4 watts. Oh, right. I see. I was thinking it was going to be like 9 volts across the resistors, but no, you do the calculation here to get the voltage across the resistor, right? And so it ends up being that um, the 9 volts is distributed across the 4 resistors in series, because 2.25 is a quarter of the total 9 volts. Yeah, intuitively, they're saying it also makes sense that if you divide up a 100 ohm resistor into 4 equal parts, each should dissipate 1/4 of the total power. Yeah. But I don't think this is going to tell us about like static and dynamic stuff. So I don't know, man. This has been a really long stream already, like 3 hours. And some change now. Maybe I should sleep on this. Because I feel like with the static and dynamic thing, because there aren't like Wikipedia pages and like you don't see it being talked about here, I think it's just like you use the equations that we've already seen. Like we know how much is static and we know how much is dynamic for energy, right? Or wait, isn't power watts? What's the unit of energy versus the unit of power? Let me go back here. Units. The unit of power is the watt. The unit of energy. What is the unit of energy? The joule. The joule is the unit of energy. So when we talk about so many watts, the static and the dynamic, yeah, that's static and dynamic power, not energy. Okay, because that's in watts. So we've got power, and we're saying we know how much of it's static and how much is dynamic. So I mean the ratio of static to dynamic power, that's just saying static over dynamic, right? So like 10 over 90 or 1/9 for the first one, and 40 or 30 over 40 for the second one. Those would be the ratios, right? 3/4, 1/9 and 3/4. Or is a ratio like 3 to 4 and 1 to 9, I guess. But you get the idea. So percentage of the total dissipated power. Wouldn't it just be the percentage of the total amount of power? So like in the first example, we had 100 watts total, right? 10 watts static, 90 watts dynamic. We say that's a ratio of like 1 to 9, right? And it would just be like like 10%, right? Or something. Like 100 divided by 9, or like 11.1 repeating percent. And then 70 watts, so 30. So like, let's change that. Divided by 70. So like 42.85% for the i5. If I'm understanding correctly, those are my answers. 1 to 9 and 11% for the Pentium 4, and 3 to 4, 42.85% for the i5. That's the percentage of total dissipated power comprised by static power, and the ratio of static power to dynamic power for each technology. If I understand the question and I understand the stuff, like the actual physics, I guess, of it, those are my answers. But I might just be not understanding. I don't know, but those answers make sense to me. So I think I'm right. I don't know. And like I say, we did the average capacitive loads already. And I think maybe I was just off by constant factors or something, because on Wikipedia it said it was like -1 to 1 or something like that. But I mean, maybe Wikipedia is wrong too. I don't know. And then we have, if the total dissipated power is to be reduced by 10%, how much should the voltage be reduced to maintain the same leakage current? And it says, note, power is defined as the product of voltage times and current. So we want to figure out how much to reduce the voltage by to maintain the same leakage current. So the first one, we had like 100 watts of power in the total dissipated. The total dissipated power. But then it's talking about leakage current. Current is the amperes. So watts are joules per second. And joules per second like 1 volt is equal to 1 joule per coulomb. So we're saying we lower the power by 10%. And we want to know how much the voltage should be reduced by. So we've got a current value here. And we have volts here, right? And we're saying we want to keep this side of the, like this part of the equation the same. By lowering this so that it equals this value where this value is reduced by 10%. So we know the values for power. Do we have voltages here? Yeah, we do. So this one was 1.25 volts. And 100 watts of power. So first of all, using that much information, we could calculate the current before we do the change. So we're saying something times 1.25 is going to be equal to the total 100 watts of power. So if you do 100 divided by 1.25, it would be 80 amperes for the current, right? So we're saying we want to keep it at 80. And we're saying it's going to be 90 watts because that would be 10% less than 100, right? So 90 watts of power and 80 amperes. So what should the voltage be? Or do we want the difference? We want to know how much the voltage should be reduced. Well, let's figure out what the voltage should be first of all. So we know this is 80, this is 90, and we want to know this value. So wouldn't it just be it would be 90 divided by 80. So 1.125 volts, and we started with 1.25. So 1.25 volts minus 1.125 is just 0.125. So it would be, you'd reduce it by 0.125 volts, if I'm understanding correctly. And then let's do the same math for this second one here. So this one starts out with 70 watts of power total and 0.9 volts. So again, if we want to get the current out of that, we take the 70 watts of power and we divide by the voltage of 0.9. So 70 divided by 0.9. So 77.7 repeating amperes. And then we're saying we want to keep this at 77.7 repeating. And then we want to say 10% less than the 70 watts of power. So like 70 times 0.9 would be 10% less, 63. So we're saying 63 watts equals something times 77.7 repeating. So 63 divided by 77.7 repeating, 0.81, so then 0.9 minus 0.81, so like 0.09 is the amount the voltage should be reduced by. So those are my answers for 1.8. Let's move on to 1.9. Assume for arithmetic load, store, and branch instructions, a processor has CPIs of 1, 12, and 5 respectively. Also assume that on a single processor, a program requires the execution of 2.56 times 10 to the 9th arithmetic instructions, 1.28 times 10 to the 9th load store instructions, and 256 million branch instructions. Assume that each processor has a 2 GHz clock frequency. Assume that, as the program is parallelized to run over multiple cores, the number of arithmetic and load store instructions per processor is divided by 0.7 times p, where p is the number of processors, but the number of branch instructions per processor remains the same. So then they're saying, find the total execution time for this program on 1, 2, 4, and 8 processors, and show the relative speedup of the 2, 4, and 8 processors result relative to the single processor result. Then they ask, if the CPI of the arithmetic instruction was doubled, what would the impact be on the execution time of the program on 1, 2, 4, or 8 processors? And then, to what should the CPI of load store instructions be reduced in order for a single processor to match the performance of 4 processors using the original CPI values? Okay. So, let me see here. So we're approaching 4 hours now. I think I'm going to call it here, and we'll continue tomorrow night. So we'll do this problem tomorrow. So we didn't get all the way through it like I was hoping, but we made a pretty big dent in the problems. And we will continue another day. So, thank you everyone who tuned in tonight. I don't think anyone stuck through the entire thing, but thank you anyway, if you watched any of it. And thank you everyone who watches on the YouTube archive, which is available at risky.tv. And you can follow me at HMN_risky on Twitter to get updates about the series. Lately, I haven't been posting schedule information, though, because I'm pretty bad at sticking to a schedule. And I'm kind of thinking about switching things up, too, so that might, it might change. I don't know. We'll see how that goes. But yeah, you can follow me there to get updates about the series anyway. And thank you everyone who supports me on Patreon. And speaking of Patreon, I have shout outs to do, so I'm going to do that right now. I need to give a shout out to David Butler. So thank you, David Butler, for your support. And I also want to give a special shout out to Jerome, because he has increased his support. I'm not gonna shout out the value, but he has increased his support. He's been supporting me from the very beginning as well, and he always leaves nice constructive comments on Patreon and such. So I just want to give a big thank you to him. That it's greatly appreciated. So those are the shout outs I have today. Yeah, I think that's everybody. And if you would like to support what I do, you can do so at patreon.risky.tv. Oh, I remembered now. I was like, David Butler, that's Croatia, isn't it? I think that is Croatia. Let me learning about. Yeah, so this is Croatia, and he is David Butler. So yeah, thank you, Croatia, for the support. And if you, viewer, would like to financially support what I do, you can do so at patreon.risky.tv. And like I say, I showed you guys, I'm working on a calculator program for programmers. And, if you want to get your hands on this when it's done, I'm going to be using it a lot on the series. I wish I had it today, obviously. It would have been very nice for what we were doing, because today has pretty much just been calculations. But yeah, if you guys want to get your hands on that, like I say, it might be a while before it's ready for shipping to people, but it's going to be, if you back me $5 or more on Patreon, you'll get access to that. So that's one little incentive for you. If you're considering backing me, you will get access to that when it's ready. So yeah, with that said, I will see you in the next episode, and stay risky, everyone.